Students, let us start today's lab class. Today we are working out with the experiment number 5. Write an HDL program for the following designs. One is 4-bit binary to gray converter, and the next one is 4-bit binary comparator. First, let us deal with the binary to gray converter. So there's a brief theory here. Binary to gray code conversion method strongly follows the XOR gate operation between binary bits. So you can see this method here. We keep the MSB as it is. The upper one is binary, the lower one is gray, starting from MSB. We keep the MSB as it is, and then MSB is XORed with writing applications. There are many varied applications for gray code. So this is the method for vectors. A and B are vectors, whereas these three outputs are single bit, which means if A is greater than B, and there is a space that is missing here, that is a typo error. You will have to assume a space here. In space standard logic vector 3220. So binary is 4-bit input. Even output gray, that is G, is 4-bit. This is the end of entity. Architecture BG1 of B2G is begin. Now with B of 3 XOR B of 2. G of 1 is assigned with B of 2 XOR B of 1. G of 0 is assigned with B of 1 XOR B. Because we already know the Boolean operations here. We need not write a behavioral type of description here. That's So network is connected. Let me resume. Let me show you the Xilinx screen. You are seeing the Xilinx screen, and I have already have the code here for binary to gray conversion. Let me select this. I have put both the codes in advance here. So for this binary to gray conversion, I have already checked the syntax. Let me add new source, Verilog test fixture, and let me write it as b2g underscore test dot v. So this is the test bench. Let us add stimulus here. Let us give the same stimulus which is there in the manual. Let me add some more stimuli just for the sake of verification. Let me add 4 more, where I'll change now. Let's change all these to 0. Now you can see there is this b2g underscore test, below which you can see the module, main module. Let us check syntax for the module once again, and let us check syntax the test bench. Now let me simulate the test bench. So this is the simulated output. You can see corresponding to 0, 0, 0, 0, output is 0, 0, 0, 0. Now corresponding to 1, 0, 0, 1, output is 1, 1, 0, 1. Corresponding to 1, 1, 0, 1, output is 1, 0, 1, 1. Corresponding to 1, 1, 1, 1, output is 1, 0, 0, 0. This is the respective gray code for the binary code. Similarly, at the end we had added 4 more here. Corresponding to 0, 0, 0, 1, output is 0, 0, 0, 1 only, because you can see all the MSBs are 0 here. Now corresponding to 0, 1, 0, 1, output is 0, 1, 1, 1. Similarly, other 2 inputs. Now this is the simulated output for binary to gray conversion. Now let us synthesize this. Let me come to the implementation window. Let me select this, and let us see the RTL schematic. So you can see a block, 4-bit input, 4-bit output. This is binary to gray. Let me double click on this, and let me zoom out. You can see one mux here, one more mux here, one more mux here. We are unable to see the circuit there because this is a RTL schematic. Now let me see the technology schematic. In the technology schematic, okay, again let me zoom out. You can see 3 LUTs here, and you can see the last one as it is going directly. See, the MSB is going there directly, and for the other three bits we have 3 LUTs. So first LUT, you can see the XOR gate only. This is now A bar B plus AB bar, and there is the XOR gate. For all other LUTs also you will see XOR gate only. For the third LUT also, you will see XOR gate only. So it is basically 3 XOR gates and MSB is going directly. This is the synthesized output for binary to gray. So now, let me proceed with the lab manual for the next experiment. Let's discuss the 4-bit binary comparator. I'll tell you the logic of this program when I discuss the code itself. Vhdl program library IEEE use IEEE.standard logic 1164 entity COMP is port A and B are inputs 4-bit, and you can see A LTB, A EQB, A GTB are outputs. These are all single bit. A LTB means A less than B, A equals B, then A GTB means A greater than B. These are the 3 output bits. End of the entity. Architecture C1 of comparator is signal x3, x2, x1, x0. We are actually declaring 4 intermediate signals. Now begin. X3 is assigned to A of 3 XOR of B of 3. Now whenever we compare 2 binary numbers, always we have to first check with the MSB. When we first check with the MSB, we will come to know whether MSBs are equal or greater or lesser. In the MSB itself, if we take a decision, let us say A is having 1, B is having 0 there. Immediately we can come to a conclusion, A is greater than B. So that is how we have to start with MSB itself. So now we are using this XOR operator. Why we have to use the XOR operator? The point is, in XOR the output is 0110. In XOR the output is 1001. That means in XOR, if 2 bits are same, then output is 1. So we can easily check for equality here. Equality is the easiest operation here now. That is why x3 is assigned with A of 3 XOR B of 3, x2 is assigned with A of 2 XOR B of 2, x1 is assigned with A of 1 XOR B of 1, and x0 is assigned with A of 0 XOR B of 0. Now, if we add all these 4, that is A equals B, x3 and x2 and x1 and x0. If this is 1, this is 1, this is 1, this is 1, then A equals B is 1. Imagine if all the 4 bits of A are equal to 4 bits of B, we are getting these 4 intermediate signals. Now, when we add all these 4 signals, naturally 1 and 1 and 1 and 1, A equals B will be 1. If it is not equal, then out of all these 4 signals, one of them will not be 1, right? Any one of them will not be 1, depending upon the case. So it is very easy to check the equality operation using XOR function. Now, how to check A greater than B? You see here, A greater than is assigned to A of 3 and not of B of 3. You can see here, it is A of 3 and not of B of 3. First, we are checking with the MSB itself. Let us say A of 3 is 1 and B of 3 is 0. The not of B of 3 is 1. That becomes 1 and 1. Okay. If that is satisfied, let us say this itself is satisfied, then we come to an immediate conclusion, A is greater than B. Otherwise, this will not be 1, right? A of 3 and not of B of 3 will not be 1 for greater than condition. Next, from MSB, we have to move to the next bit. That is A of 2 and not of B of 2 and x3. Why? You can see this x3. Here MSB, when we checked, let us say MSB are 1 and 1 only. Imagine A of 3 and not of B of 3, 1 and 1 only. Then we will get this first case as 0, because not of 1 is 0, 1 and 0 is 0. So then we are checking whether the next bit coming to the MSB is being compared with the A of 2, 1 and not of B of 2 and X of 3. Here if we get 1, then at the LSB side we know that A of 2 is 1 and B of 2 is 0. In that case, even though that EX3 is not satisfying the condition, the LSB side, sorry, the next bit coming to the MSB side is satisfying the condition, then we can say A is greater than B. If this is also not satisfied, then we have to come to the next one, A of 1 and not of B of 1 and X3 and X2. You see here. And lastly, A of 0 and not of B of 0 and X3 and X2 and X1. Because X1, X2, X3 all can be same in the case of A and B, but only LSB can be different. So this is how we check for A greater than B. Now A less than B is just reverse of A greater than B. What is that? Here we made A of 3 and not of B of 3. In a reverse way, we will do not of A of 3 and B of 3. Now this is corresponding to B greater than A, or A is less than B. In the same way, we will continue not of A of 2 and B of 2 and X3 again, not of A1 and B1 and X3 and X2, and not of A of 0 and B of 0 and X3 and X2 and X1. It is the same logic which is applicable to less than operation or less than comparison. So in this way, for equals, for greater than, and for less than, we have defined a particular functionality. All this is in the data flow type of description. We can write this in the behavioral type of description also, simply by using greater than, less than, equal to symbol. That is easier than this actually. Okay, but we thought anyhow, this is a combination circuit. Let us try to write a data flow description only for this. Even the behavioral type of description is possible, let us try out data flow only. Even the typing work is more here. As I've been telling you earlier also in the theory classes, always data flow description is depending upon the particular design. Sometimes data flow description can be bigger than the behavioral type of description. At that time, it is easy to use behavioral type of description. But at times, data flow description itself can be compact. As we have seen with the binary to gray code conversion, data flow description code itself is compact. So we can choose multiple options or multiple styles. Now this is the end of architecture for binary magnitude comparator, and this is the test bench in Vhdl. Let me proceed with the Verilog program. Module, comparator, A, B, then A, LTB, A, EQB, A, GTB. Then input A and B are 4-bit vectors, output 3 are bits. Then we have those intermediate signals there. We declare them as wires here in Verilog, X3, X2, X1, and X0. Now assign X3 as not of A of 3, X or B of 3. It is actually XNOR operation. In this case, in the case of Vhdl, we can directly use the keyword XNOR. In Verilog, instead, we are performing XNOR operation by XOR and the tilde symbol here. So this is XNOR. Now assign X2 is XNOR of A of 2 and B of 2, similarly X1 and X0. Now for equality operation, it is X3 and X2 and X1 and X0, similarly for greater than and less than comparison, which I had discussed already with the Vhdl program. Here you can see everywhere we are using symbols instead of the keywords in Verilog. This is the test bench code now, where we give A some value, B some value, then we check whether it is greater or lesser. Now this is the simulation output. I'm going to show you the simulation output anyhow now. And then this is the RTL schematic. That also I'm going to show you now. This is how we complete the 4-bit binary comparator. Both are in data flow model. The binary to gray converter is also in data flow model, and 4-bit binary comparator also in data flow model. So let me show you the execution of comparator. This is the Verilog code for comparator. Let me select this. Let me come to simulation. Here, let me add a new source, Verilog test fixture. Let me write it as comparator underscore test.v. So let me add stimulus here. We can add indentation so as to have uniformity in the view of the code. Of course, for the functionality, it does not matter. So now I have this test bench. There is some hierarchy mismatch here. You can see. So let me remove this because it was earlier there. Sometimes Xilinx will show this hierarchy mismatch. So let me remove this also. And now let me add the stimulus here. So I have saved it now. Now it is fine. It is hierarchy is matched now. As you know, what is hierarchy? At the top you have the project name, below which you have the FPGA chips number, below which you will have the test bench, which is also called a stop module, below which you will have the design module. It is called as unit under test here. We also call it as DUT, design under test. So let me check syntax for the UUT or DUT. Then let me check syntax for test bench. Now let me simulate. So you can see comparison here. When both are 0, 0, 0, 0, this A equals B has gone high. That you can see here. And when this is A is 1, 0, 1, 1, B is 1, 1, 0, 0, you can see A less than B has gone high. And when both are again equal 1, 1, 0, 1, A equals B has gone high. Others are 0. And when A is 1, 1, 1, 1, B is 1, 0, 0, 1, now A is greater than B, it has gone high. Lastly, when there is 1, 0, 1, 0 and 1, 1, 1, 0, A less than B has become 1. In this way, comparison is happening. So let me come back to the code and let us see the synthesis output. Let me select this. Let me come to implementation. Let us see RTL schematic. This is the RTL schematic. You can see the block where A and B are the inputs, 4 bit each, and you can see 3 bit output here, less than, greater than, equals. Now when I click on this, we will see many multiplexers and many such gates. You can see a mux here, one more mux, and you can see these gates. Let me zoom in. You can see these gates. Now this is RDL schematic. Let me come to technology schematic. You can see the block once again. Now when I click on this, let me zoom out. You can see a slightly bigger figure now with 3 plus 3, 6 LUTs. Let me show you the first LUT. You can see a big circuit here now. Even though the outputs are only 3 bits here, equals greater or lesser, but the computation, logical computation is much larger because you have seen in the data flow description, the statement is shown here. Corresponding to the statement, it is generating the logic. You can see the truth table also here for the logic. You can see the equation also here. This is the schematic. Similarly, for the second LUT, you can see one more such circuit. For the third LUT, you can see one more big circuit. Coming down to the next 3 LUTs, you can see a slightly smaller circuit here, and one more smaller circuit, and one more smaller circuit. So it has constructed 3 small circuits and 3 big circuits, and it has combined them together, and finally it is giving us the output here. You can see this A equals B. Here it is A equals B, output from LUT 5. Then A greater than B, again output from LUT 5, but it is AGTB. And A less than B, output from LUT 5, again it is ALTB. So you can see it has made use of 3 lookup tables having 5 inputs and 1 output. What about the next lookup tables? It has used here 4. It has used 3 lookup tables with 4 inputs and 1 output. So you already know that all these LUTs are internally programmable. All lookup tables are internally programmable, means inside each LUT for a corresponding input stream, whatever is the output that is accepted is pre-stored by means of programming bits. And when it is pre-stored, the pre-stored output will come out, and there is no need of any additional hardware. That is what is called as lookup table. So with this, we have come to the end of today's lab class. Today's lab class has ended slightly earlier because today's experiments, both of these experiments are slightly smaller experiments. And as such, tomorrow, as we have internal test, so what we can do is quickly write the observation book for today and upload it to the Google class. Then you can leave the class. Until then, I will stop sharing the screen, and in between, if you have any questions, you can ask me. I will stop recording also.